You ever wonder what a video game world is really made of? Or a VR space? Or even those crazy scientific models? Well, we're going to pull back the curtain today and look at the secret, invisible building blocks that make all of these 3D digital worlds tick.
Okay, we all get pixels, right? Those tiny little 2D squares of light that make up every single image on our screens. But that's flat. What happens when you go 3D? When you add depth? What's the 3D version of a pixel? What are the actual atoms of a digital world?
Well, the answer is the voxel, and the name kind of gives it all away, doesn't it? It's a mix of volume and pixel. Yep, it's basically a 3D pixel, a tiny cube that sits on a grid in three-dimensional space. The absolute best way to think about it, it's a digital Lego brick. And you know what that means? You can build pretty much anything with them.
All right, so let's take that Lego idea and run with it. First up, we're diving into the world of virtual reality, because voxels are letting us literally build and sculpt digital worlds with our bare hands. Okay, picture this. You're completely jacked into a VR world. The last thing you want to do is break that immersion by fumbling for a clunky keyboard or mouse, right? It ruins the whole experience. So the big question is, how do you build things in a way that feels totally natural? Well, that's exactly where voxel-based modeling comes into play.
So how does this actually work? Well, forget clicks and keyboards. You just use your hands. Seriously, researchers have figured out these super intuitive gesture systems. You just pinch your fingers, and boom, a menu pops up. You touch a virtual color palette. You point right where you want the next block to go. And then a little double tap, and poof, the voxel appears. It's so direct, so fluid. It's literally creating stuff with your fingertips.
And this whole idea, this way of interacting, has a name. It's called a natural user interface, or NUI for short. The whole point is to get rid of the middleman, the mouse, the keyboard, and just let you take direct, intuitive actions. You're not telling the computer what to do anymore, you're just doing it.
So here's the big takeaway for this part. When you use voxels as these simple, stackable blocks, it completely changes the game for digital creation. It stops feeling like you're coding or using some complex software and starts feeling like you're just sculpting with clay. It's that direct, that tangible. Okay, but let's push this idea even further. We've seen voxels as simple, dumb blocks, but what if each one of those blocks could be smarter? See, voxels aren't just for us to build with. They're becoming a game-changing tool for teaching computers how to see and understand the 3D world. Just think about engineering for a second. You've got literally thousands and thousands of super complex 3D parts made in CAD software. How on earth do you teach a computer to look at all that and automatically know, oh, that's a bolt, or that's a specific kind of handle? Well, the very first step is to translate that shape into a language the computer can actually speak. And yeah, you guessed it, that language is built on voxels.
Now this is where it gets really cool, seeing how our use of voxels has evolved. On the one hand, the old school way was super simple. You just slop a grid over a 3D model and ask one basic question for each voxel. Is this spot filled or is it empty? Just a simple yes or no. But now we have a much smarter approach. Today, each voxel is a powerful little container of data. It doesn't just ask if something is there, it asks a whole bunch of questions about what exactly is in that space.
I mean, just look at this. This is just a sample of the kind of information we can cram into one single voxel now. We're talking about things like the surface area of the little piece of the object inside that cube. We can measure its curvature, telling the computer if it's a sharp corner or a nice, smooth curve. We can even calculate its volume. So suddenly, it's not just a dumb block anymore. Each voxel is a tiny, detailed report on the geometry it holds. And that's the real game changer here. By packing all this rich data into every single voxel, we're not just making a blocky version of a shape anymore. No, we're creating a super detailed, data-rich digital fingerprint. And that is something a machine learning algorithm can finally sink its teeth into, something it can read and compare and actually understand.
So we've gone from building things to analyzing things. We've seen how voxels can describe the physical what, but now let's get even more abstract. Let's see how this exact same grid-based idea can be used to map the inner workings of the human brain and how it's speeding up scientific discovery in ways that are just wow. So get this, in neuroscience, when they do fMRI scans to see what your brain is doing, the data they get back is already in voxels. But in this case, a voxel isn't a piece of a machine part, it's a tiny little cube of brain tissue. And the whole goal is to see which of these little brain cubes are lighting up at the same time, which ones are talking to each other. When you map all those conversations, you get this massive web of connections called a functional connectivity graph.
Okay, but here's the catch. A single high-res brain scan can have more than 100,000 of these voxels. And to build that connection map, you have to compare every single one of them to every other one. Do the math. We're talking billions upon billions of calculations. It's so computationally expensive that it makes the analysis incredibly, painfully slow. Sometimes it's just not even possible to do.
So obviously, somebody came up with a new, faster method to do this. But that always raises the big question, right? If it's faster, is it worse? Are we cutting corners? Are we missing something important? Well, here's the amazing part. When they compared the brain maps from the old, slow way with the new, super fast way, they were practically identical. All the key connections, the main communication hubs, everything was still there. So, just how much faster are we talking about here? Check this out. The new method is 13.5 times faster. That isn't just an improvement, that is a massive, game-changing leap.
And just to put that number into perspective for you, have a look at this chart. To process a 50,000 voxel brain model, the old way took nearly a minute. With the new method, just over 4 seconds. Think about that. What used to take almost a minute is now done in the blink of an eye. And this is why it matters so much. This is way more than just a small speed bump. A speed up like this unlocks entirely new possibilities. It means scientists can finally start analyzing huge, high-resolution brain scans that were just impossible to tackle before. It's literally accelerating our understanding of the human brain itself. All right, so we've covered a lot of ground, right? We've seen voxels used for creating art, for teaching computers to see, and for analyzing the brain. Let's step back and tie all these threads together. So when you think about it, we've really seen the voxel wear 3 totally different hats today. It's been a simple building block, a complex digital fingerprint, and a tiny data point for mapping something as abstract as the brain.
And that right there is the beautiful, unifying theme. It doesn't matter if we're building the world with our hands in VR, teaching a machine to recognize a physical object, or mapping the very connections inside our minds. The humble little voxel gives us a universal grid, a common language to describe and understand our three-dimensional world.
It's such a powerful idea, isn't it? Just taking something complex, putting a grid over it, and suddenly making it understandable. This one little concept is already changing everything from art to engineering to neuroscience. So it leaves us with one big question. As our tools get even faster and our data gets even richer, what are we going to map next?